Integrating eye gaze into machine learning using fractals. Our hypothesis is that using a fractal curve to represent a two-dimensional feature space will yield better results than using a traditional snaking grid path. But what exactly do we mean when we say snaking grid path? A snaking grid path is the curved path a string of characters make as they substitute all points in a space. This particular string substitution path can be seen in work done over a decade ago in scan path comparison methods, one of which was ScanMatch by Cristino and others. If we simplify our stimulus to a 4x4 pixel space, you can see here that our origin is in the top left and in point A and ends in the bottom right at point P. If we overlay a 4-fixation scan path which starts with a fixation at point N, our scan path string in this case would be NEDK. So we now understand how string substitution works using a grid that snakes around all points in a space. How does a fractal curve do this differently? Well, unlike the snaking grid path, a fractal curve meanders around this space in this cup shape. For example, in this 4x4 space, a Hilbert curve would exhibit this shape. Hilbert curves have been used to reduce dimensionality in other non-machine learning applications, for example, softmatch by Newport and others. If we overlay the same scan path we used before in the same 4x4 space, but we use a fractal curve instead of a snaking one, our origin would be at the bottom left and end at the bottom right, and our string would be BEKN. Though unlike the snaking grid path, as the fractal path grows from a 4x4 space to an 8x8 space, the meandering path transforms and rotates, exhibiting a self-similar pattern that fractals are known for. This behavior, during its increase in resolution, assists in the preservation of locality. In order to test our fractal curve's performance against the more traditional snaking method, we employed a one-dimensional vector as our feature space. Our input feature space consisted of a vector of size n representing regions of interest over the stimulus. If a region of interest contained a fixation, it would be switched from 0 to 1. So the final feature space was a vector of 1s and 0s. In this slide, we demonstrate this via 16 regions of interest. However, in our paper, we actually used 256. Here we see a template showing input vectors for both the snaking grid on the top and fractal curve on the bottom. If we overlay the same scan path over our 4x4 unit space, we can see what the input vectors would look like using both methods. Our experiment was performed with ethics approval through Macquarie University and performed by trained staff with the consent of all participants. We used 53 medical professionals and tracked their gaze using an iLink 1000 Plus by SR Research. We did track both eyes, but we used only the right eye in our experiment in order to increase accuracy. A great paper by Hooge and others demonstrates how sometimes one eye is better than two when it comes to gaze tracking accuracy. None of the participants were art professionals and none had a high degree of familiarity with the paintings we used in our study. As you can see, the paintings are highly abstract, and one may wonder if any discrimination in eye path patterns could be made at all, especially between the Jackson Pollock paintings. But our results came to be quite conclusive. For our support vector machine trials, we wanted the machine learning methods to be as default as possible to prevent them from introducing artifacts. For this reason, we use MATLAB's FIT-CSVM to create the model and MATLAB's predict for prediction testing. We used leave one out for validation, so this resulted in iterating through all combinations to get our final result. Our test indicated that using a fractal curve instead of the traditional snaking grid path to represent our feature space resulted in better results in all tests except convergence in the convergence versus Starry Night test. And just to refresh your memory, here is convergence on the top and Starry Night on the bottom. The SVM test failure did not overwhelmingly test one way or the other, but rather discriminated both paintings equally poorly. In our convolutional neural network tests, we also used the default MATLAB approach. We added a convolution layer with a kernel size of 5x5, followed by a ReLU layer, two fully connected layers, a softmax layer, and final classification layer. We conducted our training over 500 epochs of 2 iterations each. Our final CNN results showed no snaking grid-based method performed better than our fractal method. However, Starry Night performed as good using both methods. And to refresh your memory, Starry Night looks like this painting. This stimulus performed the same using both methods and was also a stimulus in the poorly performing binary test using SVM. And as we can see by the results, with all other factors being the same, simply using a fractal curve in place of a traditional snaking curve can contribute to increased accuracy during machine learning tasks. This is due to the fractal curve's unique spatial properties and locality preservation. However, in the few cases where our fractal curves method did not perform as well, deserves some further scrutiny. Convergence, blue poles, and Pasiphae all share a high degree of contrast, abstraction, and geometric complexity, which may play a role in the degree to which they scramble visual fixation patterns during bottom-up search. These challenges in separability were resolved under CNN. However, Starry Night was still challenging for both methods and in both tests. Looking to the future, what is some new work that can come out of this study? An objective characterization of eye tracking using our method can be used to stratify patients affected by diseases, for example, dementia or autism, or to conduct follow-up tests in a longitudinal fashion, for example, tracking cognitive decline, or even to predict neurological outcomes, for example, post-operative brain function. There can also be teaching applications where radiologists searching for pathological features can be assessed based on their visual search patterns. And thank you for listening to my presentation on how we can integrate eye gaze into machine learning using fractal curves. I hope to see you at NeurIPS 2022, and best wishes from all of us at Macquarie University's Computational Neurosurgery Lab, Australia.